And does anyone have a question about the test?
Definitely did a lot better on this one than the first one.
Yep, for many people it was a lot better than the first one. But unfortunately for 2 or 3, it was worse than the first one. All right, so we're going to kick off the new life. And unlike what we had after test 1, this is different now because the topics that we are going to cover now are highly correlated with the topics that were on test 2. So you need to keep in mind everything that was on test 2 while we are solving these topics all the way up to test 3. So the method of undetermined coefficients will be a method that we use to solve an equation when the right-hand side is not 0, but has a specific form. So we will be dealing with this object. Constant second derivative plus a constant first derivative plus a constant times a function equals f of x, where f of x is either a polynomial of degree n or a polynomial of degree n times e to the alpha x, or a polynomial of degree n times e to the alpha x times cosine of beta x, or any combination of the three. Notice here, polynomial of degree n could be a polynomial of degree 0, which would just remove that polynomial from there, would just be a constant. Either the alpha x, alpha could be 0, that would just remove the exponential part. And in the cosine, if the cosine is, if beta is 0, it's just going to take us back to this case. And then when alpha is 0, it just takes us back to this case. So all the three different right-hand sides in this class, I'm going to just represent them by this only one. Or here, the last one would be Pn, polynomial of degree n, e to the alpha x times sine of beta x. So it could be, we are going to deal in general with one of these two. And it's the same method you will apply to any of them. And again, I say, if you see something like this, you know that just means that here, beta is 0, right? So anything with cosine just falls down. If you see this, that means that alpha is equal to 0. That's it. So I'm going to start by, so we get in the case 1. F of x equals Pn of x e to the alpha x. Again, Pn of x means what? A polynomial of degree n, which is Pn of x is a0 plus a1x all the way up to an x to the power n. That's what it means, polynomial of degree n. Any polynomial of that form. Now, how do we solve this? We say if alpha is not, there are two cases when alpha is not a root and when alpha is a root. Is not a root of a lambda squared plus b lambda plus c equals 0, which is the Euler equation of the homogeneous differential equation when the right-hand side is 0. So we always have to start solving this problem by first finding the solution of this equation. And that's why I say it's highly related. If you can't solve that, then you're in trouble for solving the problem we have now. So if alpha, which is the power you have here, is not a root of the Euler equation, then we look for y of x, yp of x equals Qn of x times e to the alpha x, where Qn of x is a polynomial of degree n. That means you're looking for C1 as C0 plus C1x plus Cn x to the power n e to the alpha x. And the method of undetermined coefficients actually means what? That we take this problem and then we just write down this polynomial with these unknowns coefficients C0, C1 all the way up to an. We take derivatives, and when we plug into the equation and try to see what are the values of C0, C1, Cn for which this function is a solution. And these coefficients are thus the undetermined coefficients that we are talking about in the method. You don't know them, and then you are looking for them through the equation given the form of the right-hand side that you have. So the form of the right-hand side that you have tells you what kind of function you want to try as solution. Am I making sense here?
Yes.
And you got to be very careful. Anytime you have that, make sure you check first that condition that alpha is not a root of this equation. All right. And if that is the case, then you look for that. And then what you do is take derivatives. And usually in my class, instead of saying plug into the equation, I say track the coefficients. And I'll show you how we do that. Track the coefficients of the basic functions. In this case, for example, the basic functions are e to the alpha x, x times e to the alpha x squared times e to the alpha x, all the way up to x to the power n times e to the alpha x. That's what I call the basic functions. So here, that is e to the alpha x. If alpha is 0, you see that e to the alpha x will just be 1. X e to the alpha x squared e to the alpha x, all the way down to x to the power n e to the alpha x. So we are going to track the coefficients of each of these functions along the equation. Okay? And when you do that, you solve. Solve the obtained system to find C0, C1, Cn. And once you do that, you get your answer. And then how do you finish the problem? The solution of the problem y of x is equal to capital Y of x plus little y p of x, and we call this the superposition. The principle of superposition, that's our superposition principle. So the principle of superposition means we take this is the solution, general solution of the homogeneous problem, which is obtained by whatever method we use in that on that test tube. And this is the particular solution that is found here. So you solve, you get the general solution of the homogeneous problem. You find this particular problem by solving for the C's, and you add the two solutions to get the general solution of the problem. So this is the general solution of the non-homogeneous problem. So the general solution of the non-homogeneous problem is equal to the general solution of the homogeneous problem plus any particular solution of the problem that you can find. And in this specific case, a particular solution can be found using this formula. That's all the method is about. And now the problem will be how to navigate this from one case to another. Notice that here, this is just case 1. Right. We got many cases. Any questions?
What is that last y?
Where?
In the, I guess after the plus. Which
That's
one is that represented?
even here.
No, on the bottom.
Well, I'm saying that's exactly this YP that you're seeing here.
Oh, okay.
And then if you get this right here, then the rest of the chapter is going to be easy. It's all about following these little steps here. Let me give you an example of how that works. Let's say we have this equation. And that would be the first problem in which we have a non-zero right-hand side. How do we solve it? Let me start here. First step, write down the homogeneous problem. Solve this homogeneous problem. How do we solve this? Get the Euler equation, lambda squared minus 2 lambda equals 0. Solve it using any method you want. Lambda 1 equals 0. Lambda 2 equals 2. So you got the two solutions. And so the solution of the homogeneous problem is C1 e to the 0x plus C2 e to the 2x, which is C1 plus C2 e to the 2x. So this is the solution of the homogeneous problem, which is this part of the answer. And now, on step 2, you're gonna write down YP. And to write down YP, you got to check first that alpha is not a solution of the homogeneous problem. What is alpha in this problem?
Is it just 1?
This 1, that's right here. Alpha is what is in front of x here, it's 1. So alpha is 1 in this problem. And you look at the solution of the homogeneous, it's 0, 2. 1 is not there. That's what we are checking in that first case. 1 is not a solution of the homogeneous problem. And what is n here? So right here, that's alpha equal 1. What is n here? What's the degree of the polynomial you have here?
1.
1. So n is 1 as well. That's the degree of this polynomial. So I'm going to have a polynomial of degree 1. That's ax plus b times e to the alpha x, which is e to the x. That's it. That's what the method says. Write down your YP like that. Take the derivatives and track the coefficients. And so we're going to take the derivatives, YP prime. The derivative of this is going to be ax plus a plus b e to the x. Product rule, you do that. This is what you get. And if I take the second derivative, it's going to be a plus 2a and that's ax, right? That's ax plus 2a plus b, and then e to the x. Why is that? Because it's a product rule. Derivative of this, you take derivative of that, which is a plus multiply by e to the x. Derivative of e to the x is the same thing, so you get a plus the same thing you have there. That's why it's ax plus 2a plus b. Now we got all these functions there, and now we need to track the coefficients of the basic functions, which I told you were going to be e to the alpha x, x e to the alpha x, all the way up to x to the power n e to the alpha x. N is 1, and I recommend that you always start by the highest. So that's on step 4. We're going to track the coefficients. So we start by x e to the x. That's the highest one in this list. And so how do we track? We actually follow in the equation that we have, in the equation that we are solving right here. So we follow this equation, and for each of the functions we have here, we take only what is related to x e to the x. That's what it means, tracking just the coefficients. That is to avoid having to write long lines there of derivatives that you can end up forgetting something inside there. So I start here, second derivative, and I take only what is related to x e to the x. Second derivative is right here. Ax e to the x, that's the only thing I have there. So that's a. I continue my equation, I got a minus 2, then first derivative, minus 2 and first derivative. And I go to the first derivative, I look for x e to the x, and that's another a. So that's minus 2 times a equals, and I look at the right-hand side of the equation, I have x e to the x, 1, the coefficient is. That's it. And if you follow this way of solving, the first equation is always going to give you the constant right away. You don't have a crazy system to solve. You can see here, we got a minus 2a equal 1. So we got a equal -1, right? If you do this, it's always going to come out that clean. The first equation gives you the first parameter. The second equation gives you the second. The third equation gives you the third, and so on. You don't have crazy equations to solve. Then I go to the next one. After x e to the x, it's e to the x. And that's it. Here I will have only the first two because I got only n equal 1. So I get only 2 equations to follow. Now I go follow e to the x in the equation. Again, second derivative e to the x, what is it? It's 2a plus b. So that's 2a plus b. Minus 2, and then I get into the derivative, and I look for e to the x. That's a plus b. Because that's a plus b e to the x. And then there is nothing else equal. The right-hand side of this equation says what? Is there any e to the x by itself there? Can anyone tell me what's the coefficient of e to the x on the right?
Is it just 1?
I have 1 in front of x e to the x.
Would it be x?
X is not a coefficient, x is the function. And we track the coefficient of x e to the x already. Do you see any e to the x by itself on the right?
So would it be 0?
There is 0 because there is none. There's no e to the x by itself. So the coefficient of e to the x on the right-hand side is 0. And that's a smiling 0 because it knows that it is solving the problem. Now you can have here 2a minus 2a, they cancel. B minus 2b, you got b equals 0 when you solve this. So what you get is yp of x equals a -1, b 0, so minus x e to the x. So that's the yp. And so the solution of the problem is y solution of the homogeneous problem, C1 plus C2 e to the 2x, plus the yp we just found, which is minus x e to the x. That's it. That's how the method works. Questions? Again, this is only the easiest case, when alpha is not the root of the Euler equation.
Could you explain the tracking of the coefficients again?
After taking the derivatives, we follow the equation and we report for each of the basic functions which are listed here, starting from the highest. The highest is x e to the x. We don't go higher because it's polynomial of degree 1, so n is 1. So it starts x e to the x. So you start following the equation and you report only the coefficients of x e to the x. You go to the second derivative because that's where the equation starts. Second derivative, coefficient of x e to the x, it's a. You report it. You continue with the equation, minus 2. and then you follow, you get y prime. You go to the derivative, you report the coefficient of x e to the x, and that's a. There's nothing else. Equal, you put equal, you report the coefficient of x e to the x, and right here it's 1. So you report the 1. And then you solve that equation. It's always going to give you the first coefficient. Then you go to the next basic function, it's e to the x. After x e to the x, you get e to the x, and that's all. There is no other one. And so, again, we go through that equation, and we report only the coefficients of e to the x. Second derivative with e to the x, it's 2a plus b. Minus 2, first derivative, and we report only the coefficient of e to the x. In the second derivative, it's a plus b e to the x. So that's a plus b. Equal, and we put equal, and we go to the right-hand side of the equation. We report the coefficient of e to the x. There is no e to the x by itself, so the coefficient is 0. And now you solve that second equation.
Thank you.
Work. Now you solve that second equation and you get b. Once you get b, you plug them into yp, you get yp, and then you take that in the formula to find y of x equal solution of the homogeneous problem plus a particular solution of the non-homogeneous problem. And that's it. It should be pretty straightforward. If you got the material of the second test, it'll be easy to go through this and get it right. Otherwise, I suggest that you train a little bit more on that. All right, let's look at another example. Let's say here we got example 2. And that example 2 is second derivative minus twice the first derivative plus the function equals x squared minus 3. So what is alpha in this case?
Is it 0?
0. Alpha is 0, so we won't need any exponential. We just have a polynomial. Alpha is 0, and what is n?
2.
2. So we need a polynomial of degree 2. So we need p2 of x. We need q2 of x, which is a x squared plus bx plus c. Notice that I don't need to have all the terms in between here to write down here that I'm looking for ax squared plus bx plus c. All I need is the highest power of x. That's what gives me n. And I use that n to write down a polynomial with all intermediary terms. And now what we have to do is say we are looking for yp of x. So first of all, solution. And in step 1, we solve the homogeneous problem, minus 2y prime plus y equals 0. So we write the Euler equation, which is lambda squared minus 2 lambda plus 1 equals 0. And this gives us lambda 1 equal lambda 2 equal 1. And if the two are equal, then we have that the solution of the homogeneous problem is c1 e to the x plus c2 and x before e to the x because the root repeats. Now we're done with that first step. You solve the homogeneous problem. Second step, you got to write down the formula of yp of x. And yp of x, we just said, is just ax squared plus bx plus c because alpha is 0 and 0 is not a root of the Euler equation. The Euler equation has roots 1 and 1, so 0 is none of it. That's why we can find this yp. Now in the third step, we can take the derivatives. So take derivatives 2ax plus b, second derivative 2a. And then on the first step, you're going to track the coefficients. And the way we track the coefficients here, we always start with the highest. N is 2, so we start by x squared e to the alpha. Alpha is 0, so it's just x squared. Tracking the coefficients of x squared along this equation, you start second derivative. What is the coefficient of x squared in the second derivative?
Zero.
0. My derivatives are here. Second derivative is here. There is no x squared here. So the coefficient is 0. Minus twice the coefficient of x squared in the derivative.
0.
0 as well, because there's no x squared in the derivative. Plus original function, the coefficient of x squared,
A.
a, equals right-hand side coefficient of x squared, right-hand side of the equation, coefficient of x squared,
1.
1. That's it. And I said before, this always gives you what the true coefficient, the first coefficient is. So that's 0 minus 0 plus a. So you get a equal 1. And then you go lower, you get x now. You track the coefficient of x starting from the second derivative. Coefficient of x in the second derivative. Dakota?
What's that?
What's the coefficient of x in the second derivative?
0.
0, because there is no x there. That's the second derivative. In the first derivative, minus 2.
And that'd be 2a.
2a, that's it. Plus y in the original function, coefficient of x.
b.
B, that's it. Equal, right-hand side of this equation, what's the coefficient of x?
0.
0, because there isn't. That's it. And this always gonna give you the second coefficient, as I said. So you got b equal 4a, and a is 1, so b is 4. Right? Now down from x, it's 1. Because that should have been e to the alpha x, but alpha is 0, so it's just 1. And then we go again to the second derivative. Second derivative, coefficient of the constant is? What's the constant we have in the second derivative?
Wouldn't it be 2A?
That's 2a, correct. Minus 2, derivative, what is the constant?
B.
B. Plus, in the original function, what's the constant?
C.
C. The right-hand side of the equation, what is the constant?
-3.
-3, that's it. And we are professionals. That's the thing. You just follow that and everybody's happy. You get the right answer in less than a minute. So you know A, you know B, so you use them to get C. So right here, that's gonna be 2 minus 8 plus C equal -3. So C equals, and that's gonna be -5 plus 8, 3, right? Am I correct?
Yes.
So that's it, that's what we get. So with this, we got yp of x equals x squared plus 4x plus 3, which leads to the solution of the problem, general solution, equals solution of the homogeneous C1 e to the x plus C2x e to the x plus x squared plus 4x plus 3. Now, those who usually want to fight these methods often, and there are always people who try to fight that to do the way they want, you find yourself into trouble because you try to guess something and it doesn't work. And you realize it doesn't work after spending 15 minutes of your test on it. And you don't have time to do otherwise. And then you shout that the test was long. But the person who did what was required still had like 10 minutes left. He didn't know what to do with, right? So you got to be very careful. If you don't want to follow what we are doing, make sure you master well the other things that you think might work on these problems, because these are perhaps the shortest answers you can provide to these questions. They are straightforward, they are short, you try to understand them, you get them, and you easily use them. You have any questions on this other example? Now I'm going to give you a crazy example that shows you why it is important to have that condition there, that alpha is not a solution of the homogeneous problem. Let me restart this very problem that we had and just change a little bit the right-hand side. Let's say we still have y double prime plus 2y prime plus y equals, but this time I say it's equal to x e to the x. Okay, that's what I said is equal. And now I remind you, okay, here alpha equal 1 is a solution of the homogeneous problem. So the current method does not apply. So if you don't check that condition and you go ahead and you apply this method on it right here, what we just did, you're going to get it wrong. And you only realize when you solve the whole thing and you figure out there is no way you can get the answer. And sometimes actually, even after going through it, some students don't realize because they're forced to get the answer. But there is no way you can get the answer if you just apply it the way we did. Why is that? Because technically this function, x e to the x, is a solution of the homogeneous problem. Okay, so in this case requires a different plan, which is plan number 2. Alpha is a root of the Euler equation. Of multiplicity S. Remember how I used to emphasize the number of times a root is a solution. It's very important because that comes back right here. In this case, we will look for yp of x equals x to the power s first, where s is the multiplicity being the number of times alpha is a root of the homogeneous problem times a polynomial of degree n times e to the alpha x. Okay? So you will have to first multiply it by x to the power s before you start solving. In this example, s is 2 because 1 was a double solution of the Euler equation. S is 2 because 1 is double solution of lambda squared minus 2 lambda plus 1 equals 0. That's the reason why S is 2. So you would have yp of x equals x squared times ax plus b because n is 1 in this polynomial, as the right hand side is s, x, so it's power 1, that's why we got ax plus b, x squared because s is 2, and then e to the alpha is 1, so that's e to the x. And so that is ax cubed plus bx squared. I cross multiply before I start solving the problem. Okay, so that's how it works in this case. And now we take the derivatives again, and we track the coefficients. And the coefficients that we're going to track here will be x cubed, e to the x, x squared, e to the x, and all the way down, x e to the x, and just e to the x. So that will give you 1, 2, 3, 4 equations. And you might think, hey, how am I going to get 4 equations and I have only 2 constants in there? The good news is your first 2 equations, in this case, because s is equal to 2, your first 2 equations that you will write must give you 0 equals 0. If that's not the case, then there is something wrong that you're doing. So those first 2 are going to give you 0 equals 0, and you're going to use the last 2 to find A and B. Now let's do it. So we take the derivatives, right? First thing first, derivatives. So y prime of x is technically the derivative. So that's a x cubed plus b x squared. And then the derivative of this is gonna be 3a x squared plus 2b x and all of that e to the x. Why am I doing this? Because the derivative of e to the x is e to the x, right? Because what I'm doing here is taking the derivatives using the product rule. And so we have this, and then the second derivative is going to be, again, the derivative of what is inside plus what is inside, because the derivative of e to the x is e to the x. So that's ax cubed plus bx squared plus 3ax squared plus 2bx plus the derivative. So that's going to be 3ax squared, 2bx, 6ax, and 2b. And after that 2b, you multiply by e to the x. So this is what that derivative is going to give you. So we get the first derivative, we get the second derivative, we get the function. And so are we ready to track the coefficients? So on this example, you might want to understand why I say that it's better to track the coefficients instead of saying that we take these derivatives, plug into the original equation, right? And try to simplify. Do you see that? I would have to copy all this again into the equation, copy all that into the equation and try to see what is going to cancel. I have a high chance of missing something if I start doing that, right? That's the reason why I recommend just leaving those derivatives as is, and then just go ahead and just track the coefficients, because it's easier to just follow what is happening to x cubed e to the x throughout the equation. What is happening to x cubed e to the x? And always start by the ones with the highest power of x, because that helps. And so we go to the second derivative in the equation, start by the second derivative. Coefficient of x cubed is a. And once you get rid of something, you can cancel it in there to make sure you see that it's gone. So second derivative x cubed, gone, a. Minus twice the derivative x cubed, gone, right there. Minus twice a. Plus the original function, x cubed, a, also gone. Equals right-hand side of the equation, x cubed e to the x, there isn't. Because the right-hand side of the equation is just x e to the x, right? So none. Remember I told you that this equation is going to give you 0 equals 0. A minus 2a is minus a plus a is 0. So that is really 0 equal 0. Again, let me emphasize here, this is where most of the time some people mess up. If you don't listen to what I say, right here, they force this equation to give a equals 0. There is no way a can be equal to 0 here, the only solution, because it's 0 equals 0. All the a's have disappeared. Everything has disappeared. You can't solve this. Anything is a solution. So don't force it to get a solution that you continue using. I always say this, and I always find one or two people that just get that and do just what I said not to do. Now go to x squared e to the x. X squared e to the x, there we go. That's 1, that's bx squared. Any other one? Nope. B, another one here, 3ax squared, 3ax squared, so that is 6ax squared. That's for the second derivative. We don't have any x squared e to the x anymore there. So we move on to the first derivative. X squared, that is b. That's another x squared plus 3a. Then plus the original function, x squared, the original function has coefficient b. And on the right-hand side of the equation, we just have x e to the x. So here is also 0 on the right. And as predicted, this must also be 0 equals 0, because the first two equations, when x is equal to 2, the first two equations are going to be 0 equals 0. Look, b minus 2b plus b, that's 0b. 6a minus 6a, 0a. So this is 0a plus 0b equals 0, always true. So you don't solve for b then. There's no way you can solve for b. And I always recommend to do these two first, because when you write them down, you can actually see if you have a mistake in your work or not. You have a mistake, you're not going to get it this way. Something is going to be messed up in these equations. Then we get down to x e to the x from x squared, and we track the coefficients of x e to the x. So we look 2b, so that's 4b. Then we got 6a. That's it. No more x e to the x. Then minus 2, we go to the derivative and we find 2b. Plus, we go to the original function, x e to the x, there isn't. So that's 0 equals the right-hand side of the equation, x e to the x has coefficient 1. This is the right-hand side of the equation. That's the right-hand side of the equation, x e to the x. And so, like I said, this equation is always going to give you the first coefficient. So you must know that 4b minus 4b, they cancel. So this gives you 6a equal 1. So a is 1/6. Like I said earlier, it's always going to give you right away the coefficient you need. Are we good? Then you get down now to follow the coefficients of e to the x. And notice that the key to all this is that you actually find the correct derivatives, right? Because you mess up your derivatives, there's nothing else you can do. Second thing, notice there is no x anywhere in these equations I'm writing. I'm tracking their coefficients. X shouldn't appear anywhere. If I have any x showing up anywhere, then I'm doing something wrong. So now let's go track the coefficients of e to the x. We go to that second derivative. Oh, what is left there? What is left there is 2b. That's all, nothing else, just 2b. So you have 2b. And then I cut this off. Minus 2. I go to the derivative, look at the coefficients of e to the x. There isn't. There's nothing there. So that's 0. We go to the original function that we are using in this problem. That's this. What's the coefficient of x e to the x? There isn't. It's 0. So that's plus 0 equals right-hand side. The coefficient on the right-hand side is 0 as well. And that one will be a smiling 0. So you get 2b equals 0, and that gives you b equals 0 in this problem. So you get yp of x equals a is 1/6 x cubed e to the x, because b is 0. And then the general solution of the problem is c1 e to the x plus c2x e to the x plus 1/6 x cubed e to the x. So this is the solution of the problem. Any questions? And here we got the two cases, the case when alpha is not a solution and the case when alpha is a solution. And we had an example with S equal 2. You could have another example with S equal 1. Let's say we have a problem of this kind, y double prime minus 3y prime plus 2y equals e to the 2x plus x squared. So this is our problem. And right here on this example, I'm going to teach you something else. Now, actually, when your right-hand side is written as a sum of functions, and you are looking for yp of x, then you need to find yp of x for each of those functions. So here, we have two different types of special case here. So this is the first one, and that is the second one. So we need yp of x for each of them. Separately. So you need to consider each of them separately to get yp for that, okay? But in general, we do have, if we are solving this, the Euler equation is lambda squared minus 3 lambda plus 2 equals 0. And that gives you lambda 1 equals 1, lambda 2 equals 2, using your quadratic equation. So you get y of x equals c1 e to the x plus c2 e to the 2x. And then when you want to get yp1 of x, for this case, if I want to write down yp for this case, the case of e to the 2x, alpha for that case is 2. Alpha is 2. And I check, is alpha a solution of the homogeneous problem? Right here. We together? Is alpha a solution of the homogeneous problem? Yes, for this case, if I'm picking this one, alpha is 2 and it is a solution. How many times is it a solution?
Once.
Once. So it's only 1. So S equal 1. So that would be x to the power 1 times, what's the degree of the polynomial here? This is the part I'm talking about. What's the degree of the polynomial that is in front here?
0.
0, because it's a constant. So we are just going to look for one constant here, and then e to the 2x. If I'm looking for the second one, yp2 of x, then what is alpha here for this one?
Two.
Alpha, not n.
Would it be 0?
Alpha is 0. Alpha is what is in the exponent. You don't have exponent, so alpha is 0. So in this part, this is completely separate from the one. You see a plus in between them. So that's one case, that's a different case. So alpha here is 0 and n is 2. Now alpha is 0 and you check, is 0 a root of the Euler equation? No, because the roots are 1 and 2. It's not a root, so for this part, we are using the first case of the lecture. So it's just going to be a, because I use a here, I can't use a anymore, so I'm using b x squared plus cx plus d. That's what it's going to be. And no need to multiply by x to any power because alpha equals 0 is not a root here. And so we are going to have yp of x is the sum of these two yp. Again, that's what we call the superposition principle. So yp of x is going to be 1 plus that. So that's ax e to the 2x plus bx squared plus cx plus d. So that's what yp of x is going to be. And now if you want to solve and find it, you take derivatives, track the coefficients. And if we want to track the coefficients here, we are going to track x e to the 2x. We are going to track e to the 2x. We are going to track x squared, x, and 1. So we have 5 equations to track here. Now we start by, we want to do that, and we're going to take first the derivative. So yp prime of x derivative, that is a times a derivative of this is going to be 1. So 1. And the derivative of e to the 2x is 2e to the 2x. So that's plus 2x e to the 2x. Derivative of bx squared is 2bx plus c. Then you take the second derivative. Derivative of this is 2. Derivative of e to the 2x is 2 times that. So that'd be 2. There's 4x e to the 2x. And the derivative of this is 2b, derivative 0, that's it. So here are our derivatives. And now you can go ahead and track your coefficients. X e to the 2x. You go second derivative, x e to the 2x, that's 4a. And we can cancel it. Minus 3. You go to the derivative, you got 2a. And we can cancel it. We go to the original function, that's a. times 2, because in the equation you got a 2 there, so 2a equal 0. In the right hand side of the equation, you don't have any x e to the 2x. And notice that here s is 1, and therefore the first equation is going to give you 0 equals 0. And that is 4a minus 6a, 2 minus 2a plus 2a, 0. So that equation is 0 equals 0. It's not going anywhere. Then you come and track e to the 2x. And that's where you'll find a. Tracking e to the 2x, that's going to be 4a minus 3. And then e to the 2x is a plus 2. You go to the original function, you got none of it. Equals right hand side of the equation, e to the 2x is 1. So right there, you get a equal 1. Now you get down and track x squared. Second derivative x squared, none of it. Minus 3 derivative, none of it. Plus 2 original function b equals right hand side of the equation, x squared coefficient is 1. So you get b equal 1/2. Then you track the coefficients of x. Second derivative, none of it. Minus 3. First derivative, 2b. Plus 2. The original function, x is c, equals the right hand side of the equation has no c, has no x. So we got c equals 3b. So that c equals 3/2. And now you go to the constants. Second derivative, that's 2b. b is 1/2, 2b is 1. Minus 3, you go to the derivative, constant it's c, plus 2, you go to the original function, that's d, 2d, equals, there's no constant on the right. C also here is 3/2, so you can as well replace that, so 3/2. And so you solve that to get d. And this is going to be 2 minus 9/2, so that's 7/2. It's going to be 7/4. So you get d equals 7/4, and you got all your coefficients. Therefore, you can get y of x equals c1 e to the x plus c2 e to the 2x plus a x squared, a is 1, b 1/2 x, nope, I was messing up something here. That is not x squared, but x e to the x, right? X e to the 2x. That's a x e to the 2x plus 1/2 x squared, and c 3/2 x, and d 7/4. Again, I repeat, here it's x e to the 2x. That's it. Questions? Again, on this third example, I just showed you that when your right-hand side is a combination, what you need to do is to find the YP for each of the parts separately. Write down that formula of YP separately. Make sure you don't mess up. Notice that here we had to multiply by x to the power 1 because e to the 2x, because 2 was a root, but the second one didn't have to be multiplied by x because e to lambda equals 0 is not a solution here. So you don't have to multiply everything by x just because one of them is a solution of the homogeneous problem. You follow the rules. Look at each of them separately. For this case, we needed to. For that one, we didn't need to. Any questions? All right, if there is no question, then that's good enough for me. And next time we will look at the cases that involve cosine and sine.
Thank you.
Welcome.
Thank you.
See
Thank you.
Thank you.